Okay, kids. So this is going to kind of wrap up chapter 28. Now that you've done the photoelectric lab, this will kind of make sense now. So what I have here is kind of one of the great mysteries that they had to solve when they started looking at emissions and absorption spectrums. So basically what happens is this: when you get something to emit light, okay, so let's say, for example, it's hydrogen gas, whatever that is, okay? So it doesn't make any difference. So what's going to happen is that you have two different types of spectrums. You have an emission spectrum and you have an absorption spectrum. So on the emission spectrum, basically what happens is that you've got an electron sitting in some ground state, and you hop that electron up to an excited energy level. Now, not to the point that it completely leaves the atom like it does in the photoelectric effect. This one you just hop it up to a higher energy level. Now it becomes unstable and then it comes back down. So when it makes this jump down, that emits a certain photon with a certain amount of energy. So what they had to figure out is that when these electrons orbiting a nucleus, how can they exist in only discrete energy levels? Because if the electrons could exist anywhere at any energy level, then every atom in the world would emit a continuous spectrum, because you can think of it as like being a ramp. So if the electrons could exist, and here's your nucleus, so here's your what's called your ground state, okay? So if the electron could exist at any point at any energy level, then it could make a continuous set of jumps and you'd get a continuous spectrum. But the better analogy is to imagine that you are here at your ground state. But imagine this in terms of like steps, okay? So here is your ground state, and then here's like this first energy level. So it's either going to gain enough energy to jump all the way up to here, or it's not. It can't go halfway in between. The same thing is true here, the same thing is true here. So what happens to create this emission spectrum is that these electrons are moved up to a higher energy state. They're unstable, they come back down, they have to give off light. Now, so this is where you can analyze the light and you go, oh, okay, E equals HF, or E equals HC over lambda. So if you can look at this light and go, okay, wow, here is a band of red light. Okay? Well, red light has a relatively long wavelength and a relatively then low frequency, so it has a low energy. So what that red band of light would indicate is that somewhere in here, this atom, well, we'll even go red to get the visual effect. So this electron within this atom can absorb this energy level, and it can go from here to here, and it can kick out a red light. Now, because it's red light, and that's low energy, that means that electron didn't make a very big jump. Now, if you take that electron from the ground state up to that second energy level, that's going to get a bigger change in energy. Well, that bigger change in energy might correlate with that band of yellow light. Now, I'm going to warn you now, this yellow is bad to look at, but stay with me here. So this jump from here to here is going to emit that yellow light. Then, once you get into the greens, the blues, the purples, the higher that energy is, that means the bigger these jumps are going to be, okay? So this is the main idea, is that these electrons can only exist in quantum states. They're at the ground level, they move up, and then the bigger the jump, okay, the bigger the change in energy, the short, oh, I can't keep writing in yellow, that's just bad. The bigger the jump in energy, then the shorter the wavelength and the higher the frequency. But because, and this is the most important thing that you have to get, because of the fact that you are only seeing distinct bands of light, that means the electron is existing in only distinct energy levels. It's not a continuous spectrum. Okay? Now, that actually helped out, because that would explain why, here's the nucleus and here's this electron, okay, why doesn't this electron just continuously lose energy and end up in the nucleus? The reason it doesn't continuously lose energy and end up in the nucleus is because of the fact that it can only exist in certain energy states. Since it can only exist in certain energy states, that's why it can't fall into the nucleus. Now, this is where de Broglie plays into this. Now, this would be cooler if I could actually show you this, but imagine this. I'm going to try and draw this. Imagine that I've got a strip of paper and I've got like a wave drawn on it, okay? Now, imagine that I'm going to take this piece of paper and I'm going to curl it up into a circle. But I'm going to curl it up where I can only complete a wavelength. Now, so imagine that I've curled this thing up. Okay, so this is where de Broglie plays into this, since electrons have waves. So if you calculate a de Broglie wavelength, so imagine this is wrapped around. So I've taken this piece of paper and I've lined it up where the beginning of one matches up with the beginning of the next one. So imagine this is this point, okay, and imagine that is that point. Now, what I've done, and this is looking down from on top, okay, so here's my nucleus. Here's this piece of paper, and that circumference is one wavelength. So here's the beauty of how this played out, is that once they were able to, these were incredibly difficult measurements to take, I mean, because you're trying to find, you know, again, we can't look at an atom underneath the microscope and go, okay, yeah, oh yeah, here's this little electron traveling around in here. We couldn't. We had to find a very, very unique way to measure this diameter. But what they found is that the de Broglie wavelength matched the exact circumference of an electron orbiting a hydrogen atom. So at this point, it was a huge aha moment, because they're going, oh, this is why the electrons don't fall in. This is also why they exist in energy levels. Because if this is like your ground state, then now imagine that I'm going to take this piece of paper, and now I'm going to line this point here up with this. So now, if you imagine this is your one wavelength, now imagine I'm going to build a second one that has a circumference of two wavelengths. Now, that's why you're going to have that other distinct energy level, because I can only line up where these electrons or these wave functions reinforce each other. I can't have the crest of one meeting like at some point over here. It won't reinforce itself. It won't have that point of resonance. So if you think back to like the tuning fork lab, where we had that tube and we would raise and lower that and it would hit that point of resonance, that's basically what's happening here, is that we're hitting that point of resonance where this wavelength is reinforcing itself. That's why it can only have certain distinct energy levels. Now, here's how this plays out. So a lot of times what you'll be given is an energy diagram. And so let's say that here is n equals 1, and we'll call that the ground state, and just call that 10 electron volts. And here's n equals 2, and maybe that's at 40 electron volts. And then we're at n equals 3, and maybe that's 90 electron volts. And then we go up to n equals 4, and maybe that's 160 electron volts. And then here we are at 0 electron volts. And this is the ground state. Not to be confused with ground chuck, otherwise known as hamburger. Okay, so let's say that we're going to have an electron that's going to go from 1 up to 3. So we've got to give it this amount of energy. So we want to figure out how much energy that's going to be. Okay, so that's going to take us from 10 up to 90. So if we're going in this direction, somehow or another, if I take 90 minus 10, I get 80. So this is going to absorb 80 electron volts. Maybe that's a thermal energy. Maybe it comes from an electric current being passed through and exciting the electrons. Something is happening to make that jump. Now, in terms of an absorption spectrum, okay? So if you look at, and I'm going to kind of erase some of this so we can see this absorption spectrum. So what happens in an absorption spectrum is kind of like a negative of the emission spectrum. So what happens is that you're going to shine all of this, you're going to shine a continuous beam of light onto a cold gas. And what's going to happen is that these electrons will say, wow, hey, here's an 80 electron volt photon coming in. Oh, okay, right. So it's going to hit a cord, and that 80 electron volt photon coming in then is going to get absorbed, and it's going to make that electron go from the ground state up to here. So on an absorption spectrum, this is why these two are like negatives of each other. So on an absorption spectrum, you shine every color of light on it, but what you'll see is you're going to see gaps. So those gaps are where those electrons are absorbing that energy that match up with your emission spectrum, okay? So now, once you get that electron up here, it goes, whoa, this isn't cool. I'm going to jump back down to here. So then it's going to kick out an 80 electron volt photon that's going to match up with that. Now, so here's what you want to look at. On the way up, this electron can only go from the ground state up to here. That's it. Now, on the way down, it can actually stop. So in terms of an absorption spectrum, the absorption spectrum can only go from n equals 1 to n equals 3, which would be an 80 electron photon. But on the way down, it can actually stop in between. So what it can do is it can stop here. Now, if it makes this transition, then from here to here, that would be a 50 electron volt. Then if it goes down from here, that would be a 30 electron volt. So what you'll see is that emission spectrums will be more complex than absorption spectrums, because on the way down, it can stop in between and go, whoa, I'll stop here for a little bit, maybe grab a soda, and kick out a 50 electron volt photon. Then it's going to go, well, I still got to get back to my ground state. So then it's going to make this transition and kick out a 30 electron volt. So what you're going to be able to do, and this is what you've got to do like on this assignment that you'll see. So you've got these different energy levels, and you want to calculate the wavelength. So what I would recommend, I'm sorry, excuse the sneeze. When you're trying to calculate these wavelengths, use that 1240 electron volt nanometer thing, and then divide that by your electron volts, and then get your emission spectrums in nanometers. It's going to make life so much simpler, okay? It really will. Because some of you are hung up on joules, and God bless you, but you're going through a god-awful amount of work. So I'm just telling you, it would make life simpler if you just did that. Okay. All right. So on this assignment, question number 25 is going to talk to you about, or ask you about, if some of you have seen Star Wars and the idea of teleporting someone. And Bo, beam me up, Scotty, right? Which sounds really, really cool. But here's the problem if you think about it, and this is basically your answer to question number 25. So it's a short philosophical discussion. So your answer to number 25 is the problem with this is that it's the Heisenberg uncertainty principle. So let's say that you want to beam up, let's say, I don't know, Mia. Okay, so we're going to beam Mia from one point to another. Okay, Mia, I know you're excited about this. So we're going to, but to do this, we'd have to know the exact location of every electron, proton, and neutron that makes up Mia. Okay? Then we'd have to take, and we'd have to store that somehow. We'd have to map that location. So we'd have to know with a very, very high degree of precision where every electron, proton, and neutron is that makes up Mia. Then we're going to have to take that, all of that matter, and change that into energy. Okay? Which right away is a little bit problematic. So we've got Mia, and we get the cool sound effects and the swirling light that looks really, really cool, right? So we've changed Mia into energy. Then we're going to beam that energy, kind of like light, to someplace else. And then we're going to stop that energy, slow it down into a confined space. Then we're going to have to take that energy and then recombine everything so that we end up with Mia and not, like, I don't know, a Funyun, okay, which would be really odd. Mia is fun, don't get me wrong, but I really don't want to change Mia into a Funyun. So, but to track that, and if you've listened to me read the story about Alice in Quantum Land, once you try and narrow down the position of a particle, you have to sacrifice its momentum because of the Heisenberg uncertainty principle. So we can't have both of these. So it's like if we try and narrow down where everything is with Mia, then we're going to lose the uncertainty in the momentum. Or we can say, well, we're going to know about the momentum, then the position gets a little bit dodgy. So that's going to be the problem. So when you go to answer question number 25, and just kind of give that some thought. And I apologize because every time I give this speech, somebody who is a huge Star Trek fan goes, oh, Mr. Burkamp, man, that's another dream shattered. It was like, okay, that's my job. Okay, get over yourselves. That's my job. So anyway, just kind of give that some thought. And I'm going to send out the this is last assignment out of 28-3. And then tomorrow, which is not due, I do not want this back. You all know this drill by now. So the plan is then on Friday, I'm going to give the last lecture. I'm going to send out the last assignments. And then Monday we'll go over the last stuff for the review. Tuesday will be the last test, and then we'll call it good. So anyway, that's the story, kids.